C'est le paper by Francesco Berti, Ulrich Brera, Thomas Peters, and François Xavier Standard. Francesco will give it.
Okay. Thank you for this presentation, for this nice presentation. This is a joint work with Thomas Peters and Professors Olivier Pereira and François Xavier Standard. We will talk about how decryption leakage will affect authenticated encryption. Our main objective is to obtain ciphertext integrity with randomness misuse and leakage in both encryption and decryption. In this talk, we will provide a new definition, ciphertext integrity with misuse and leakage too, which is an extension of ciphertext integrity when there is also misuse of the randomness and leakage in both encryption and decryption. A new mode of operation, DTE2, which achieves this security notion. And we will analyze the confidentiality of this mode of operation when there is leakage in decryption. We can think about a simple scenario where there is an update of the firmware. What the adversary has in this situation is he has ciphertext of the encrypted firmware. He can, since he is updating his device, he can have a lot of leakage when he decrypts this firmware, this ciphertext. And what we want, that the adversary is not able to forge and so create a valid update with perhaps malicious Trojans inside. And after that, he is not able to recover the plaintext because there can be security property rights about the code. This is a particular issue. In fact, there are at least 2 papers talking about this, where they use the decryption leakage to recover ciphertext, plaintext from ciphertext. In my talk, I will start giving the background. Then I will talk about authenticated encryption with decryption leakage. I will talk also why previous countermeasures did not work. And we will end up talking about confidentiality with this new notion of eavesdropping with decryption leakage. This is the well-known ciphertext integrity security property, where the adversary has access to an encryption oracle, which he can query on input randomness in the message, obtaining a ciphertext, and a decryption oracle which outputs either valid if the outputs either invalid if the ciphertext he asked to decrypt is not valid, or the correct decryption. We do not want that the adversary is able to create a new ciphertext, C star, which is fresh and valid. That was a notion in the Decryption model, but as the previous speaker told, there is also side-channel problems, because when they are implemented, the cryptographic computation can leak information about the plaintext, the key, and so on. We will use a very particular model. We will suppose that one component is leak-free. This does mean that it gives no information about the key. We know that it is low, we know it is a bit unrealistic, but we can think about, for example, an AES with higher order masking, and although it is very slow, since it will be used only twice per encryption queries, this is not a great problem. For the other components, we do not need leakage protection for even if we want to provide integrity. We need a little leakage protection if we want to provide also privacy, because they must resist only simple section attack. One example of this idea is this scheme provided in CCS 2015, where we have the leak-free component, which is the dark box star, which is we will use the key because we use only the master key at the start to provide a new ephemeral key, which will be used either to compute a second ephemeral key and so on, and we will use to compute a random value, which is serves the message to obtain the ciphertext. We will see that the ephemeral keys are only used twice in all the life of the algorithm, so we need that to provide privacy that this F, simple with no, which are not leak-free, are able to resist only an attack where the adversary is able to ask only the encryption of true plaintext. While the master key, it could be used in every encryption queries. Now we will add leakage in ciphertext integrity, and we will obtain the ciphertext integrity notion with leakage in encryption and randomness misuse. We allow the person to control completely the randomness, and when he asks encryption queries, he will obtain not only the valid ciphertext, the real ciphertext, but also the leakage. If again, we do not want that the adversary is able to provide a valid and fresh ciphertext. Since we want misuse resistant, we need that every bit of the ciphertext will depend on the full plain text. So we will use a mode of operation which we propose in a paper which has just been accepted in SSS. And we will start the testing where we hash the randomness in the message, obtaining a value H, which will be used to be tagged with the leak-free component. And with this tag will be used to start the rekeying process. And we will obtain the first ephemeral keys. We have the leak-free component. Then we will use the scheme, the previous scheme. We notice that we will encrypt the randomness. This is to have better CPA property when there is leakage for the hash function. Now, when we have to decrypt, we have to start from the tag. We will recompute the first ephemeral keys from which we can decrypt, because clearly it's only to invert the position of the XOR. Then we will obtain a candidate randomness and messages, which will be hashed, and we will compute the valid tag for this hash. And we will check if this tag check which we computed is the tag the adversary provided. We proved in that paper that it is misuse resistant, is ciphertext integrity with misuse and leakage secure, and it's also CPA resistant even if there is leakage. But we were able to to see that we were not able to provide authenticity when decryption leaks, because we can use, if we have a randomness in the message, we can compute ourselves the correct hash for this function. Then we will ask the decryption of the ciphertext where the hash is the tag. We will obtain by leakage this first ephemeral key, which will be now asked another decryption of the ciphertext where this first ephemeral key is the new tag. So we obtain the first new ephemeral key. And now we have the correct tag for this H value, and also the first ephemeral key for the value we computed before. Before to solve this problem, I wanted to give you the new security notion, which is ciphertext misuse and leakage in both encryption and decryption. Now the adversary not only you receive leakage when he asks encryption queries, but also when he asks decryption queries. So when the adversary asks a decryption of a ciphertext, we obtain the message, or invalid if it is not valid, and the leakage of this computation. Now we wanted to provide this, to give a scheme which provides this security notion. And so first we started to avoid the previous attack. We're tweaking in this way. We avoid the previous attack because now we have made these two leak-free components and distinguish completely random from each other, because we use a one-bit tweak. So now the previous attack won't be used, because if we ask now the decryption of a method where the hash is, where the tag is a hash value, is no more equal to this value when the hash is here. But this is not a sufficient countermeasure. In fact, we are able to provide an attack where our objective is to obtain this chain where we have the randomness, the message, the hash of this randomness and messages, the valid tag for this hash value, and then the first ephemeral key. What we can do first to get the correct tag. We will ask the decryption of a random ciphertext. We will obtain via leakage the randomness in the messages. Then we will obtain via leakage, and we are also able to compute ourselves the hash value. And since the algorithm to check authenticity will compute the valid tag to check, we can obtain via leakage this valid tag. Now, having all this, we need only to know the first ephemeral keys. But what we can do is to ask the decryption of a ciphertext where the tag is the correct tag we received before. So now we obtain via leakage this first ephemeral keys. This is because when, and so we are going. This attack works because in the decryption, the adversary, the admin before computes the correct tag and then check it. So we think that we provide the solution. Instead of having the decryption oracle saying, it is not the tag you provide me because the right tag is this, which I provide you, we will say, no, this is the right tag for another hash value, which is a check. So instead of checking if the tag is the correct one, we will invert the tag, and we will check if this check value is the hash function. So we will have the correct tag for a certain h value. We suppose that asking that this leak-free component is strong PRP, that this is random, and from this value it's difficult to obtain a randomness in plaintext for whose HC is the correct tag, is the hash function. We will call this notion range-oriented privilege resistance. Now we have, and this solution works. Now we have talked about authenticity. I will talk really briefly about confidentiality, because we define the paper a new security notion, which is proper when with decryption leakage, and we want that the leakage of ciphertext does not help distinguish other ciphertext or to know information about the plaintext of other ciphertext. And we propose a new mode of operation, which is called encryption DGS and tag, which provides this new notion, EAFDL, and ciphertext integrity with misuse and leakage. But we lose the misuse resistance. To conclude, we have proposed two new definitions, ciphertext integrity with misuse and leakage, and is proper with decryption leakage. We provide two modes of operation, which achieves misuse resistance and ciphertext integrity with misuse and leakage, in both encryption and decryption, but we lose this EAFDL. If we want to have this EAFDL, we have to lose misuse resistance or to use a third call to the leak-free component, which can be a problem because, as I already said, they are very small. Thank you for your attention. Any questions?
Okay, we have some time for questions. Any questions? All right, no question. I do have one question. It looks like it's getting quite expensive to get proper security for these things, right?
Yeah, it's true, but what we do is only two calls for this heavy protected for the full encryption. So even if it is really expensive, you can afford also to have 2 seconds for this call because they are only twice for the whole encryption queries, because the other are simple AES, which are really fast. So is this why we decided not to have a leak-free components every way, because okay, this is a trivial solution, but unrealistic.
Okay. If there are no other questions, let's thank the speaker again.